Okay, hello. Nice to see you.
Good afternoon, Professor.
Hi. So as I promised last time, we will have a discussion of partially filled capacitor with the dielectric, and then we will proceed like afterwards we will proceed with electric current. So we will consider a new topic today. Good, so let me change the screen. And let us consider a case when we have first some parallel plate capacitor with a thickness D, and the space between two plates is filled with, like, there's nothing, there's vacuum. It possesses some capacitance epsilon 0 and sorry, this C naught, and there is some area of the plates A. So let us consider what is going to happen when we partially fill this capacitor with a dielectric, which is adjacent to one of the electrodes. So in this case, let's assume that the thickness of this part with vacuum is 1 minus F times D, and the thickness of this dielectric will be F times D. So there is some coefficient F, which we will discuss in details. Will change in different ranges and see what the result it will have on the capacitance of this system. So we can represent this partially filled capacitor as two capacitors connected in series. This will be capacitor 1, capacitor 2. So first capacitor will be filled with dielectric and its thickness will be F times D. And the other will be empty, and distance between plates will be 1 minus F times D. So we'll have C1 and C2 for their capacitance. So obviously we can represent some like this system of two capacitors in series with some equivalent capacitance C, and this is our task to understand how to calculate this equivalent capacitance. So let's write here down the capacitances for C1 and C2 expressions. So we know from the equation which we derived for parallel flat capacitor, parallel plate capacitor, that we will have with dielectric constant K. So this dielectric possesses some dielectric constant K. It will be K times epsilon 0 times A divided by the distance between electrodes, and here it's F times D. So then we have C2. This is just parallel plate capacitor with vacuum inside. So it will be epsilon 0 times A divided by the distance between the electrodes, will be 1 minus F divided by D, like times D. Okay, so now we can proceed for the calculation of the effective capacitance of this system of 2. Will be 1 over C equal to 1 over C1 plus 1 over C2. This will be F times D divided by K epsilon 0 A plus 1 minus F times D divided by epsilon 0 A. This is equal. We can factor out D divided by epsilon 0 A. D divided by epsilon 0 A. So here we have F divided by K plus 1 minus F. And we can put in the common numerator. It will be D epsilon 0 A F times plus 1 minus F times K divided by K. So we can now write the expression for the capacitance. This is equivalent capacitance. It will be 1 over this expression. So C is equal to epsilon 0 A divided by D times K divided by F plus 1 minus F times K. Okay, so now we have this expression. What else we can do? You see that here is, this is actually our C0 capacitance of the capacitor before we put the dielectric inside. So partially fills the space between two plates with this dielectric. So we can actually write K times C0 divided by F plus 1 minus F divided by K. So this is the final equation which answers this question, what will be equivalent capacitance. And now we can consider two cases. So first, let's consider F approaches 0. So what do we have then? So it will be 0 plus 1 minus 0 times K. So it will be K divided by K, we cancel out. It will be just C0. So capacitance will be approaching C0, and that's natural because if we set the thickness of the dielectric close to 0, then it will approach just initial condition when we have empty space between the parallel capacitors. And also another case, it is when this thickness, like this coefficient in front of thickness, approaches unity. So it means we fill our capacitor completely with the dielectric. So if it's equal to unity, then we have unity plus 0 times K. So it will be actually capacitance will approach K times C0. So it will be just a K times larger capacitance than capacitance of the empty capacitor. Okay, with this, I think we are done, and now we can proceed further with the new topic, which is electric current. So So far, we were considering always some equilibrium conditions, and one of the requirements for this is that we don't have any net charge transfer. So it always randomly moving in the volume of conductor or on the surface, but there is no some predominant direction for charge transfer. However, when we don't have equilibrium conditions, we have some flow of charges, and this flow of charges is called current. So definition of current, actually when we have some electrical charges, we have some surface, like cross section, for instance, of a wire, and these charges are moving in the conductor perpendicular to this cross section. So it means that some current, which is marked as I capital, exists in this conductor. And in general, some current is defined as some, let's say, call it average current, is defined as the rate at which electric charge is flowing through some surface. For instance, cross-section of the wire. And so we have change in the electric charge, delta Q over delta T. So this is a definition of electric current. If, for instance, current is a function of time, then we need to deal with so-called instantaneous current, which is defined as derivative of charge over time. So the units for electric current from this definition, it is Coulomb divided by second. And it has some specific unit for it. It's called ampere and marked as capital A. So this is the units we use to describe, quantify electric current. And if we consider, so in order to have some electric currents and net motion of charges, we need to realize certain conditions. So first of all, the material should be conductive, so it should possess some free charge carriers which can move. And also we need some potential difference, which will be the driving force for this current to flow. For instance, metals, that's like most common conductors, they possess electrons, which can move all over the volume of the conductor and participate in charge transfer. So if we take some metal wire and connect its beginning with the end, there is no electric current because there is no potential difference between the beginning and end of this wire. However, if we connect such a wire with a battery, then there will be electric current. Why? Because this battery will create potential difference between the edges of the wire, and that will push the system, the conductor, out of equilibrium condition. So it will perform some work in order to move these charges. So let us consider some microscopic model of current, and let's assume we have some cylindrical conductor. It's like one cross section. Here is another. Let's call it A and A prime. They are the same in area. So we consider some charges inside this volume defined by two cross sections. and distance between them is delta x. And charges have quantity q. And they are moving with some velocity vd. So in this case, how do we define the electric current? So first we need to define how much of charge is located in this volume element, which is A times delta x. So for this, we need to know concentration of charge carriers. It's N, measured in units centimeter minus third, or power, or meters minus third. So it's how many charge carriers we have per cubic centimeter. And then we multiply by this volume and charge of the single charge carrier, Q. Yeah, also keep in mind, I forgot to mention it, that the direction of electric current is conventionally considered as the direction of movement of positive charges. So if positive charges create electric current, then electric current, direction of electric current, and its drift, like velocity of these charges, will be in the same direction. However, if charge transport is transported with negative charges like electrons, then electric current and drift velocity will be in different directions. We will discuss a bit more later about drift velocity, and we'll give more clear definition of it. So now we can write that electric charge delta Q is N times A times delta X times Q. So this distance delta X can be represented in another form. It can be V d times delta T. So delta X is equal to V d times delta T. This delta T is some small interval of time. And for our consideration, it's useful to consider so-called tau, which is time interval between two successive collisions of charge carrier with the atoms in the crystalline lattice of the conductor. So it's really very, very short interval of time, and we can definitely operate with this. So we can write here that our electric charge will be N times A times Vd delta T times Q. And our average current, in this case, it will be delta U over delta T. And it will be concentration of charge carriers times electric charge of a single charge carrier times this Vd, so-called drift velocity, times area. So this is the expression for the average electric current, considering concentration of charge carriers and their drift velocity. Also, obviously, it depends on the cross-section. The larger cross-section of the wire, then at the same drift velocity and concentration of charge carriers, we will get higher current. So drift velocity is some average velocity of charge carriers in the direction of electric field, like internal electric field, which already exists in the conductor. Because so far, again, I focus your attention here. We were talking before about equilibrium conditions. and claim that electric field is equal to 0 in conductors, inside conductors, the volume of conductors. However, since we are dealing now with electric current, so we're dealing in the condition which is out of equilibrium. And here electric field is not equal to 0. So that's why drift velocity is some average velocity of electric charges along the internal electric field lines inside the conductor. That average velocity charges gain because of Coulombic like electric force acting on these charges in this external electric field. So let us proceed further and introduce resistance, electrical resistance, like conductivity and resistivity. So usually it's convenient to deal not with the current, but with the current density. So it's shown, it's denoted as capital J, and this is equal to the ratio of current to the area. And in this case, it will be N times Q times VD. So what is nice about current density, we are not attached to the features of the conductor, like geometrical features of the conductor. So we don't have area here anymore. So it will be defined only by the properties of the conductor material and potential difference between within this conductor. So this can be also written in another form, which is equal to sigma times E. And this is the Ohm's law in differential form. So keep in mind that Ohm's law is not some universal law which works always. It works only under certain conditions, and this should be taken into account because when so the statement of the Ohm's law is that the ratio between the electric current density and electric field in the conductor is always constant and equal to the sigma, which is called conductivity. So this is true for many cases, like many metals or some pristine materials. They possess this feature and follow, like obey Ohm's law. However, in some cases, we have field dependent conductivity, and then we claim that the behavior of such conductor is not ohmic. So let us consider this on an example of resistance. So let us introduce resistance. So consider some cylindrical conductor with some cross section A, some electric field E, and there is some current I. And we have two, like at the edges of this segment of conductor, we have potential VA, and here potential VB. So we have some potential difference between these edges. So delta, assuming that we have uniform electric field, the difference in potentials between these two edges will be electric field times the length of this segment, L. At the same time, we can write for the current density that it's equal to the product of conductivity times electric field. And electric field can be expressed from this equation. So we will get sigma times delta V divided by L, length of this segment. Now, let us express delta V from this equation. So it will be delta V, difference in potentials between edges. It will be L, length, divided by sigma times so will be times J, yeah, current density. And this can be represented also in form of electric current. So here we operate with electric current density, but we know that electric current density is equal current divided by area. So we can substitute now instead of electric current density, electric current, this will be L times sigma times A and times electric current. And this can be written as R times electric current times I, electric current. So this R is electrical resistance, and it's equal to L divided by sigma times A. So we have what we can write now. We can write like Ohm's law in the differential, Ohm's law in the integral form. So it can be, let's say, electric current is equal to potential difference divided by resistance. And here is an example of an ohmic conductor. So we have voltage, like potential difference, and here we have current. So what does it tell? It tells us that if this conductivity follows Ohm's law, like Ohm's law, then we have current voltage characteristics. So when we have current versus voltage potential difference, it's called current voltage characteristic. So we have linear current voltage characteristic. So at negative potential difference, at positive potential difference, we also always, so here is 0 for current and potential difference, we always have linear dependence. And this slope, like delta current, and here is delta V. So the slope delta current divided by delta V will give us 1 over R, 1 over resistance of this conductor. So if we have some, now I would like to give you some example of non-ohmic conductor. So that could be very good example, would be some diode characteristic. So we will consider this in future, but I just want to give you an example. So here is voltage, current, and diode characteristic, current voltage characteristic made feature is not symmetric feature. So it means that at negative potential difference, electric current is very small and almost saturated. It doesn't change with voltage. But at forward bias, it increases exponentially. So here, current is constant. And here, current is proportional to E in the power of V. So this is very asymmetric current voltage characteristic. Obviously, it's not linear. And we can claim that such like semiconductor diode doesn't follow ohmic law in terms of describing its current voltage characteristic. So there are different materials and devices which do not obey the ohmic law. But this is true for many materials. So let's go to another slide. And we didn't introduce the units for resistance. So units for resistance are actually voltage divided by ampere, and it has some specific unit, which is ohm, and marked as capital Greek omega letter. So electrical circuits possess many resistors, and they are used there to define the magnitude of electric current in different parts of electric circuits, and they play like very important role. So there are many different resistors with varied quantity, like varied resistance. So these elements are called resistors, and they possess different resistance and also different can dissipate different power. So they can be huge, tiny, and most popular are and commonly spread so-called SMD resistors, which are really tiny and automatically can be placed on electric circuits. And we have plenty of those in our smartphones, computers, and any like modern electronics. So now, since we know the definition of electric resistance, it would be useful to introduce the also another parameter, which is specific resistance. And this is 1 over sigma. So it's reciprocal value parameter for the conductivity. And with this parameter, we can write in more usual form expression for the resistance, which will be specific resistance, so it's specific resistance or resistivity called times L divided by A. So what do we see here? That electrical resistance increases linearly with increase of resistivity, rho, and that is defined by the property of the material. So it's a material property, specific resistivity. That's why it's called specific, because it is not defined by geometry of the conductor, only by properties of the conductor. And here we have geometric features like length and cross-section area. So now, by using this equation, let us calculate resistance of insulator of coaxial cable. So let me share the screen so you see the model for this case. So we have such cylindric empty cylinder with 2 conductors inside and outside, and some plastic insulator between them. So radius of this central hole in this cylinder is A, radius of the cylinder is B, and taking into account the cylindrical symmetry of this case, it is convenient to operate with, in terms of length, consider radius. So we consider radius at some distance from the, which defines the distance from the center, and then delta R, like small change in radius, which defines certain volume of the insulator. Since we have electric current lines going perpendicular to the surface of this cylinder, in all directions symmetry, we have this cylindric symmetry, we can apply this approach and integrate over R, over the radius position vector. So coming back to the slide, let us now realize these calculations. So we know the specific resistance, radius of the internal hole in this cylinder, and radius of the cylinder, and also length of this cylinder. So dr, like small resistance or a small element of this cylinder, would be considered as rho times dr divided by so it's considered as instead of L, and here we have area, and we need to consider side area of this cylinder. It will be 2 pi times R, the length of the base of the cylinder, and times L. Okay, now we need to integrate this expression to get resistance of such coaxial isolation, coaxial cable isolation from A to B, which is internal and external radius, times rho dr 2 pi r L. We have constants here, so we can take it out from the integral. Will be rho divided by 2 pi r. Oh, sorry. We integrate over r. Cannot take this out. So it's L. Here, integral from A to B, dr over r. And this integral will be rho divided by 2 pi L, natural logarithm after integration, b divided by a. So we had natural logarithm b minus natural logarithm a, and difference of the logarithms is equal to the logarithm of the ratio. So this is the final expression for the resistance of such a cylindrical insulator. Now let us go and discuss in more details the model of electrical conductivity in, let's consider some metals. So in this case, since we know there are free electrons which can move within the volume of the metal conductor, they are treated as some atoms of ideal gas. And what happens with them, that they randomly move in all directions and interact time to time, like collide with the atoms of the crystalline lattice. If they we have some internal electric field, so the system is not in equilibrium condition, there is always some electric force which acts on these charges, Q times electric field, and definitely they will gain some kinetic energy due to this force, but this model of conductivity assumes that the electrons give this energy back to the crystalline lattice while they interact, like collide with the atoms of this lattice. And that means that they lose the kinetic energy they gain because of electric field acting on them. And at the same time, this energy transfer causes increase in temperature of the metal. is increase, and that's why when we have some electric current passing through conductor, it starts to warm up. So these effects will be quantitatively considered a bit later. So now let us focus on this electric force. And obviously that when we have some resultant electric force, like some average force which acts on the charge carrier, it will be equal to the, according to the second law of motion, product of mass and acceleration. So acceleration can be expressed as the resultant electric force times, so divided by mass. So in case of charge carriers, like in electric field, we can write that this is equal to Q times E divided by ME. ME is effective mass of electron in this crystalline lattice. So it may be different from mass of free electron in vacuum because of effect of this crystalline lattice on the way how charge carriers are moving inside this metal. But it usually kind of close to the value of mass of free electron in vacuum. So we assume that we have a constant electric field, and that means that our acceleration will be also constant. So if we consider acceleration constant, then we can calculate final velocity. It will be initial velocity plus acceleration times t, some time. And that is equal to v initial plus q times e divided by me times t. So now we can, again, I mentioned previously that this short interval of time can be substituted by tau, which is time interval between two collisions, like successive collisions of charge carriers with the crystalline lattice, like between the moments when it gives back all kinetic energy it's gained, charge carrier gain while moving in freely in this external electric field. And also what we need to take into account that this initial velocity, before we turn on the electric field, as I mentioned before, we assume that these charges are moving randomly, so in all directions. And that's why when we calculate some average internal velocity, it will be equal 0 because it will go in all directions, and some average value will be 0. So that's why we can write that final velocity is equal to so-called drift velocity, Vd, and this is equal to this like second term times tau, this time interval between two successive collisions will be q times e divided by me times tau. So we know that current density is J equal to NQ times VD. And now we can substitute instead of VD its expression for the magnitude of this. So now we operate with the speed, not with velocity. We assume that we have just one dimensional case. N times Q square times E divided by ME times tau. And now we can actually a bit restructure this. It will be N Q square times tau divided by ME times E. And this part can be represented as sigma. So now we have an expression for specific conductivity, sigma. So sigma is equal to NQ square tau divided by ME. And also we know that there is specific resistance, like resistivity. It's 1 over sigma, and this is equal to ME divided by NQ square tau. So these are very important expressions which describe ohmic type of conductivity. Why? Because we see that for this expression of sigma and rho, we don't see any field dependence. So N is a property of material, concentration of charge carriers in the unit volume. Tau, it's again the property of the material. It's how big and closely located are crystalline lattice atoms in crystalline lattice of this, which build this material, and it defines how efficiently charge carriers are going to be scattered on these sites, and effective mass of electron in this is also material property. It defines by the crystalline lattice. So we don't have electric field in these expressions for conductivity and resistivity. So if conductivity is maybe better like this, if conductivity is not a function of electric field, then we can claim that the conductivity which is realized in this particular example follows, like obeys ohmic law, and it is ohmic. So now we just shortly consider temperature dependence of specific resistance. Usually for most of pure metals, not alloys, but pure metals, you can see such temperature dependence of resistivity. So it's rho naught times unity plus alpha T minus T naught. So we have some linear dependence of resistivity on temperature. So so let us consider first these parameters and then discuss the reason for that. So here, this rho naught, it's some specific resistance at some reference temperature T naught. So usually it can be different. It can be either 0 degrees Celsius or like 20 degrees Celsius. These are like kind of calibrated values at calibrated temperature. And then rho, it's specific resistance at any given temperature. So this coefficient alpha is defined as 1 over rho naught times delta rho over delta T. And this one is called like temperature coefficient of resistivity. Usually it is independent on temperature. So if it's just pristine metal, for most metals within wide temperature range, this temperature coefficient of resistivity is not dependent on temperature. And that's why we get linear dependence of resistance and temperature dependent linearly dependent resistivity as a function of temperature. So the same could be written for the resistance. This is equal to, like, R is equal to R naught times 1 plus alpha T minus T naught. This is also valid for temperature dependence of resistance, because resistance is actually defined by the resistivity. So for metals, concentration of electrons is not a function of temperature, since the metals don't have any band gap. Concentration of free charge carriers in the conduction band is independent on temperature. That's why resistance linearly increases with temperature, because the oscillations of atoms in the crystalline lattice start to increase while we increase temperature. The more these atoms move around, the higher probability of interacting with electrons, and electrons start to collide with these oscillating atoms in the crystalline lattice more frequently. So more frequently they lose their gain kinetic energy in external electric field, and it becomes more difficult for charge carriers to move through the conductor. And that's why resistance increases. However, there are some materials like semiconductors where there is a gap, energy gap between conduction and valence band, and the concentration of charge carriers which can participate in charge transfer, like free electrons or holes in case of semiconductors, also positively charged particles. Their concentration depends on temperature exponentially. So N is, well, it's proportional to exponent minus EG divided by KT. K here is like Boltzmann constant. This is temperature, absolute temperature, and EG is the band gap, the energy gap between some materials parameter which defines the energy distance between the valence and conduction band. So in this case, since concentration exponentially increases with temperature, we also have this linear increase of resistance because of scattering on oscillating atoms at higher temperature. But linear increase in resistance is negligible in comparison to exponential increase in concentration of charge carriers. And since concentration of charge carriers comes here in nominator for conductivity and the numerator for resistivity, if we have huge increase in concentration of charge carriers, then we definitely have huge decrease in resistivity of this material. So for semiconductors with increase of temperature, resistance, like resistivity, significantly decreases. So it becomes, this material becomes much more conductive. So that should be taken into account, this relationship between electrical conductivity and properties of the material. For different materials, it will behave in a different way. Okay, so that's pretty much everything I wanted to tell you. For instance, some practical application possible, just for fun. You can calculate the resistance, the temperature of the filament, like tungsten filament in the electric bulb. So you can measure resistance of this electric, like light bulb before, and you turn it on, and after you turn on, obviously resistance will increase because its tungsten will be at much higher temperature. So resistance will be much higher. If you know resistance at room temperature and at working temperature, you can find this alpha in literature. It's some parameter like of the material, this temperature coefficient of resistivity. And from that, using this equation, you actually can determine temperature, working temperature of this filament at which this, for instance, halogen light bulb is working. For instance, they are used quite often in for illumination at home or also in cars. That's an easy way how you can calculate this temperature, because there is no option to measure it directly. You don't have access to this wire, and the temperature is so high that most thermometers are not capable of measuring such high temperature. So you can see that this could be found some possible applications in real life, this temperature dependence of electrical resistivity. Okay, thank you very much for attention. I think we are done for today. Remind you that we have midterm tomorrow, so be ready. Read all problems. Find the most simple problems, solve them first, and then spend the rest of the time trying to solve other problems which are more difficult. So be sure that you secure at the beginning all possible points and then try to get more. Yeah, any questions? You're welcome.
No, thank you.
Yeah, thank you very much for attention, and good luck with your midterm. So take care and have a good evening.
Thank you. Goodbye.
Bye.